So we're going to develop a few more equations. We really have three equations. We have this one for the position. We have this one for the velocity and the acceleration. Right? And then we developed a third one which said V average is equal to V initial plus V final divided by 2. And so I'm going to develop two more equations that are going to be allow us to do problems like the last problem in one step. And so I'm going to start with this equation. For the first one, I'm going to say, look, V equals V naught plus the acceleration times the time. And I'm going to add V naught to both sides. So I'm going to say plus V naught. And this becomes V plus V naught equals 2V naught plus the acceleration times the time. And then I'm going to divide both sides by 2. And this, you'll recognize, is just the average velocity. And so this is V average is equal to, if I divide that by 2, I get V naught plus 1/2 the acceleration times the time. And now if we look at this V average and look at a different version of this equation, V average is equal to x minus x naught divided by time. And I can substitute that in here, and I get x minus x naught divided by time is equal to V naught plus 1/2 the acceleration times the time. I'm going to cross multiply the time, and I'll go up here, I get x minus x naught is equal to V naught times the time plus 1/2 the acceleration times the time squared. I multiply both sides by time. This guy gets a time and this guy gets a time, which makes him a time squared. And then I can write this as x equals x naught by adding x naught to both sides plus V naught times time plus 1/2 acceleration times time squared. Right, and I would call this equation 4. I'll write them all on one screen in just a minute. And so I've got one more to do, but before I do that, I'm going to go back and work that previous problem we did a second ago with this equation and show you I can solve it in one step. Okay, and so let me get to that. So this is the question we had a minute ago. A car traveling at 10 meters per second accelerates at 2 meters per second squared for 15 seconds. How far has it traveled? And last time, we first had to calculate the final velocity, then we had to calculate the average velocity, and then that allowed us to calculate the position. But notice this equation we wrote just a minute ago which combined those three equations into one, allows us to solve this immediately. I can just plug into this equation. This is my V naught, this is my acceleration, this is my time, and I can choose x naught equal to 0, or I can just move it over to the other side and say I'm calculating x minus x naught because that's how far it travels, the final position minus the initial position. And so I'll write it this way. I'll say it's 0 plus, this is 10 meters per second times 15 seconds plus 1/2 times 2 meters per second squared times 15 seconds squared. And so 10 times 15 is 150 meters per second times seconds. My seconds cancel, and I get 150 meters plus, okay, the 1/2 and the 2 cancel. And I get, so this is going to be, this 15 squared is 225. There's going to be a second squared here and a second squared there, which will cancel 225 meters. That's what we got at the end of that problem after we'd done the three steps. And so this allowed us to solve this problem in a single step. So these are the three equations we started with. X equals x naught plus v average times time, v equals v naught plus acceleration times time, and the definition of the average velocity. And I'm going to combine them all again and rearrange them slightly differently. What we're going to do is we're going to get rid of the time here. And so I'm going to start with this equation, x equals x naught plus v average times time. And then I'm going to substitute in this guy for v average. And so I'm going to write that as x equals x naught plus v naught plus v divided by 2 times time. And then for time, I'm going to grab this equation and rearrange it, solving for time. And so if I say v equals v naught plus the acceleration times the time, that means the acceleration times the time is equal to v minus v naught, or the time is equal to v minus v naught over the acceleration. And this thing I'm going to stick in for the time right there. And so this becomes x equals x naught plus v naught plus v divided by 2 times v minus v naught over the acceleration. If you do all the math here, you get x equals x naught plus v squared minus v naught squared over 2a. And you can rearrange all that algebraically and get v squared is equal to v naught squared plus 2a times x minus x naught. And I would call this equation 5. And so now we have 5 equations, and for kinematics, these are probably the 5 important equations. The first 3 were the ones we started with. X equals x naught plus v average times time. 2 is v equals v naught plus the acceleration times the time. 3 is v average is equal to the initial velocity plus the final velocity divided by 2. 4, that's just the definition of the average, assuming the constant acceleration. X equals x naught plus v naught times time plus 1/2 a times t squared. And finally, v squared is equal to v naught squared plus 2a times x minus x naught. These are the 5 basic equations for kinematics, and they're what we'll use. You should have them written on a sheet of paper. They're on your equation sheet, and you should kind of be able to get comfortable using them to solve various types of problems. Notice this is a solution for a problem that doesn't have a time in it. Like, for example, a car accelerates at 2 meters per second squared, starting from rest as it travels 100 meters. What's its final velocity? You don't have a time in that, but you can solve it using this equation. These two just depend on these 3, and so you can always, anytime you would use one of these, you can also use these 3. Just as we showed solving this problem, we were able to solve it in 3 steps. These are just kind of shorter versions, an easier way to get to a solution without having to invoke all 3 equations successively.
Get him out of here.
So a car accelerates from 20 meters per second to 30 meters per second over a distance of 10 meters. Determine its acceleration. Previously, I'd given you problems earlier where I would say it takes, say, for example, instead of over a distance, I give it over a time. So I say a car accelerates from 10 meters per second from 20 meters per second to 30 meters per second in 10 seconds. And the acceleration is just the change in velocity over the change in time. But here you have a distance now. And so you can't just do something that simple. You can't divide the difference in velocities by the distance and get the acceleration. And so we have to go back to our little list of equations, right? So first let's just say this is our v naught, and this is our v, and this is our delta x, which is x minus x naught, or in this case it's just x if we choose x naught equal to 0, right? And so you can go through your little list of equations and you can see that equation 5 on your list is v squared is equal to v naught squared plus 2a times x minus x naught, right? We're looking for the acceleration, right? This is what we want. And so we have v naught, and we have x minus x naught, right, which is that 100 meters. And so I'm looking for a. Whenever you see me work a problem, I will rearrange the formula to get the a before I start plugging in numbers. I encourage you to do the same thing. If it stresses your algebra skills, good, that's what it's supposed to do. But when I rearrange this, this becomes v squared minus v naught squared equals 2a times x minus x naught. I can divide both sides by x minus x naught, and I'll switch sides, and I get 2a is equal to v squared minus v naught squared over x minus x naught, or I get a is equal to v squared minus v naught squared over 2 times x minus x naught. There are so many reasons for doing this. First of all, it's faster than plugging in numbers and juggling them around and keeping track of their units and all of that stuff. But also, you will start seeing equations that look familiar to you. If you plug in numbers, the next problem is going to have different numbers, and so you won't recognize any of the equations again, because if you plug in numbers early, because they'll have different numbers in them. Every time you solve this equation for a, you'll get this. And I might ask you for a different quantity. You might have to solve for a different quantity. But each time, if you go through the process of solving algebraically, you will come to recognize various forms of this equation depending on what variable it's solved for. And that'll allow you to say, on a test, you might say, oh, wait a second, I made a mistake there, and you can catch it. Your eyes will recognize maybe when you've made a mistake. And so this just becomes, I can just plug in now. I want my acceleration, so it's 30 meters per second squared minus 20 meters per second squared over 2 times my distance traveled is 100 meters. Right, and so that's 900 minus 400. So this is 500 meters squared over seconds squared. Hopefully I'm still on the screen there. Divided by 200 meters. And so that gives me an acceleration of 2.5 meters per second squared. If we didn't have this handy equation here, we would have had to do multiple steps. That allowed us to do that. I could ask a few other questions about this. So I could say, so that was it. So I got A is equal to 2.5 meters per second squared. And now I can go off and I can say, question B, how long does this take, right? Well, I know the acceleration, I know v naught, and I know, v and v naught, and I have my equation 2. If you remember equation 2, it's v equals v naught plus the acceleration times the time. And so I'm looking for the time now, right? This is t equals question mark. And so since I know v and v naught and a, I can solve for t. T is equal to v minus v naught over the acceleration. Right, I'll skip the algebra for those two. And so that's 30 meters per second minus 20 meters per second over 2.5 meters per second squared. 30 minus 20 is 10, divided by 2.5 is 4. And meters per second over meters per second squared, you invert and multiply, that just comes out in seconds.